Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable and ready to wander with me into the quiet restlessness of our star, whose familiar glow carries patterns older than any human memory. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The narration settles into a slow drift above the sun's surface, where brightness softens into a textured field of convecting light. What appears from afar as a solid sphere now resolves into granules of plasma, each one rising and falling in slow, persistent cycles. The scientific fact that guides this opening is simple. The sun's photosphere churns with convection cells, hot plasma rising, cooler plasma sinking, each one shaped by the heat escaping from the interior. This surface seems tranquil at a distance, yet it conceals processes of enormous scale. Only took a few 100,000 kilometers of distance to make turbulence look like calm. The narrator lingers on the movement of these granules. Each one measures roughly the size of a continent, yet they behave like gentle waves. The bright centers rise towards space before sinking back into the darker edges, patterns that repeat endlessly with a rhythm so steady it feels almost meditative. A poetic detail emerges in the subtle shimmer that dances along the edges of these cells, where light bends through the upper layers of plasma, creating a soft, rippling glow. Only took a few minutes of rising and falling to create patterns that have existed since Earth was young. Yet a quiet scientific mystery lingers beneath this surface. While convection is well understood in principle, the exact details of how deep layers exchange heat, how turbulence becomes organized across such immense distances, and how magnetic fields interact with these flows remain subjects of ongoing research. Even with satellites observing constantly, some processes remain too complex to fully unravel. Only took the complexity of plasma to keep familiar light partly unknowable. As the narrator drifts slowly across this textured landscape, ironies settle softly into place. The sun, which seems unchanging to human eyes, constantly reshapes itself. The light that appears steady is born of continuous motion. The surface that feels warm and familiar holds temperatures so high that atoms struggle to remain whole. Only took a calm morning sunrise to hide a storm of unbound particles. Farther across the surface, the narrator observes the outlines of supergranules, larger convection patterns spanning distances far wider than their granular counterparts. Their flows are so slow that even time-lapse imagery compresses hours into brief glimpses, yet here in quiet narration, their shapes remain a steady tapestry of drifting light. These broad patterns guide the magnetic fields that rise from the sun's interior, carrying with them the seeds of activity that will shape storms, winds and radiation. Only took a few gentle currents to steer energies powerful enough to reach Earth. A modern analogy drifts gently into the scene. These convection patterns resemble the surface of gently simmering water, though on scales so vast the comparison becomes metaphor rather than likeness. The simmering of the sun is measured not in seconds, but in minutes, hours, days. Yet its patterns remain rhythmic, whispering across the bright surface like a quiet pulse. The narrator moves slowly across this glowing sea, sensing how the granules appear and vanish with quiet regularity. Their lifetimes match the soft tempo of background solar sound waves, oscillations that ripple through the sun's interior and give scientists clues about its hidden structure. The sun vibrates constantly, though no ear can hear it. Only took standing far enough away for vibration to masquerade as stillness. The narration lingers on a region where convection rises more vigorously, creating brighter patches among the granules. These regions may signal emerging magnetic fields that twist and bend beneath the surface before rising into the atmosphere above. Their presence remains subtle for now, but they will shape the transformation that lies ahead. For this moment, the sun remains in its quiet phase, its surface glowing with steady radiance, its granules flickering like a mosaic of ancient fire. Only took the sun's constant churn to deliver the steady warmth that shapes every molecule of life on Earth. Beneath this surface, photons generated in the core tens of thousands of years ago finally reach the world above, completing journeys through dense layers before escaping into space. Those photons now form the shimmering light the narrator observes. The sun's surface becomes a boundary between ages, between the deep time of photon travel and the brief moments of light that fall on Earth each day. And so the narrator remains suspended above this restless calm, letting the sun's slow, bright movements fill the stillness with a quiet pulse. Soon the story will drift deeper into the layers of light themselves, exploring the patient paths that energy follows before reaching the surface. For now, we rest above the granules, above the waves of plasma rising and falling above the star that feels familiar, yet remains older, larger, and more intricate than any world it warms. The narration drifts inward, now sinking gently beneath the luminous granules toward the deeper layers where light itself ages. The surface glow softens until it feels like a veil drawn over older radiance, and the movements of plasma slow into broader, heavier currents. In this region, the guiding sensation becomes the patience of light rising through deep time, a reminder that every photon escaping the sun's surface carries a history measured not in moments, but in millennia. The scientific fact grounding this section is foundational photons born in the sun's core do not travel straight outward. Instead, they undergo a random walk, scattering off charged particles billions of times, taking anywhere from 10,000 to several million years to reach the surface. Only took a few million years of wandering for a single beam of sunlight to reach the world it warms. As the narrator drifts downward, the scene becomes diffuse. Light no longer travels in clear lines, but in soft tangled paths bouncing between hydrogen and helium. Ions jostled gently by electrons that themselves move in response to the sun's immense temperature and pressure. The plasma here feels dense, heavy, and slow, yet it carries the earliest traces of energy produced by nuclear fusion deep below. A poetic detail emerges in the way these photons lose memory of their origins. A photon created by the fusion of hydrogen into helium never reaches the surface. It is absorbed and re-emitted countless times. What escapes after millennia is no longer the same particle, but a descendant of that ancient energy shaped by ages of scattering. Only took the journey of light to erase all clues of where it began. The narrator senses the near silence of this region, not the silence of emptiness, but the silence of overwhelming density, where motion becomes uniform and indistinct. Here, heat moves not through radiation, but by convection, beginning its long ascent. The boundaries between these layers remain partly mysterious, shaped by physics too deep and complex for simple observation. Only took the complexity of plasma to keep the sun's middle layers partially hidden, even from modern science. As the narrator travels through this dense region, ironies emerge softly. The light that reaches Earth in 8 minutes once spent eons in darkness. The star that seems immediate and familiar hides within it distances no eye can see. And the warmth that shapes seasons and climates began as energy forged under pressures so unfathomable that words scarcely contain them. Only took the quiet transformation of hydrogen to shape the entire history of life on Earth. The motions here grow broader as the narrator descends into the radiative zone, where energy travels mainly through photon scattering rather than physical mixing. The plasma moves slowly but remains stable, forming a region where heat flows outward with remarkable consistency. This stability stands in contrast to the turbulent convection above. Only took millions of years of steady outward radiation to give the sun its apparent calm. In the dimness of these layers, the narrator imagines the slow drift of energy as a kind of ancient tide, an outgoing wave that takes longer to rise than civilizations to form, break and vanish. A gentle modern analogy settles. If the sun were calm water, the photons would be grains of sand pushed upward by countless eddies, taking lifetimes to reach the surface. Farther inward, the density increases even more. At these depths, the plasma behaves neither like gas nor liquid, but something between a state of matter governed by equations that require advanced models to approximate. This region, although studied extensively, still holds mysteries how precisely turbulence transitions into radiative transfer, how magnetic fields distribute themselves across the deep interior, how minute changes in composition affect the sun's overall luminosity. Only took the basic structure of a star to create puzzles that last centuries. The narrator follows the faint suggestion of gravity, pulling downward, balanced perfectly by the pressure of fusion pushing outward from the core far below. This equilibrium, known as hydrostatic balance, defines the sun's stability. Without it, the star would collapse or expand violently. Its persistence across billions of years reflects the delicate fine-tuning of forces working in unison. Only took the constant pressure of light to hold a sphere of plasma against its own weight. The scene shifts as the narrator drifts into the tachocline, a thin, mysterious layer between the radiative zone and the convective zone above. Here rotation changes sharply with depth, generating shear that plays a crucial role in forming the sun's magnetic field. This shear generates the dynamo effect, a process still not fully understood despite centuries of observation. Scientists know it exists, know it shapes solar cycles, know it influences sunspot formation and stellar winds, yet its deepest workings remain elusive. Only took the sun's hidden rotation to create magnetic patterns that shape events across the solar system. The narrator allows this quiet mystery to linger. The tachocline acts like the hinge between the sun's deep orderly regions and its chaotic surface. It is here that magnetic fields gather strength, twist, fold, and prepare to erupt into the corona above. Yet nothing visible in the present scene suggests such potential. Everything appears slow, soft, and uniform. The dynamo's power hides in the subtle differences between layers. Only took a thin, unseen boundary to decide the rhythms of an entire star. The narrator rises again through the convective zone, carried upward by the same currents that will deliver energy to the granules observed earlier. These convective cells transport heat far more quickly than radiative diffusion, though quick here remains relative. A single cell may take weeks to rise. The large-scale patterns beneath the surface shift, slowly changing position, over months or years, and every movement contributes to shaping the surface patterns of activity. Only took a background of slow cycles to produce the brief flashes of space weather humans later observe. Approaching the surface once again, the narrator reflects on the deep time contained within a single ray of sunlight. The warmth that touches a leaf, a stone, a window pane. Its journey is a story measured not in moments, but in eras. And as this slow ascent ends, the narration prepares to drift toward the next region, where magnetic fields rise, twist, and begin the slow dance that leads to sunspots. For now, the deep layers settle back into their rhythms, patient and unbroken. The narration rises gently toward the sun's upper layers again, moving into the region where heat carried upward by convection meets the magnetic structures that thread through the photosphere. Here the guiding sensation becomes the weaving of magnetic fields in plasma, a vast slow-motion choreography of invisible lines, shaped by the sun's rotation density gradients and the subtle dynamics of charged particles. The scientific fact grounding this section is that magnetic fields in the sun are generated through the solar dynamo, a process in which plasma motions and rotation create and sustain magnetic structures that rise, bend, stretch, and realign continuously. Only took the steady turning of a star to give rise to magnetic threads strong enough to shape storms millions of kilometers wide. As the narrator drifts above the surface, the plasma reveals itself not only as bright granules, but as a medium filled with tension. Magnetic lines pierce the photosphere, forming loops that stretch into the chromosphere and corona. These loops glow faintly in observational imagery, but here they feel like soft, subtle arcs, quiet presences rather than brilliant structures. They exist because the sun rotates faster at its equator than at its poles, twisting magnetic fields into spirals over time. A poetic detail emerges in the way these lines begin as faint, gentle patterns beneath the surface before rising buoyed by magnetic pressure. Their ascent is slow, measured in days or weeks, yet they carry energy older than any human memory. Only took a slight difference in rotational speed to twist entire regions of plasma into coiled, waiting forms. The narrator watches as one magnetic loop begins its ascent. Beneath the surface, toroidal fields, sheet-like magnetic structures become buoyant due to the twisting and stretching imposed by differential rotation. As they rise, they push aside plasma like a slow bubble drifting upward in deep water. At first, nothing visible changes at the photosphere. The surface remains quiet, shimmering with its familiar convection cells. Only took countless hours of hidden motion to prepare a loop that will soon reshape a region of the sun's surface. Yet a quiet scientific uncertainty rests within this process. While models simulate magnetic buoyancy and field evolution, no direct measurements of subsurface fields exist. Heliosismology offers glimpses sound waves travelling through the interior reveal hints of hidden motions, but the full geometry of the sun's magnetic engine remains unresolved. Scientists know the broad strokes but not the intricate details. Only took the constraints of distance and opacity to keep the sun's heart partly mysterious. As the magnetic loop nears the surface, its presence begins to influence the convection above. Granules stretch and shift slightly, forming elongated patterns where magnetic tension rises. The narrator lingers on these faint distortions, subtle enough that a casual view of the sun might miss them. Only took the faintest hint of hidden force to change the patterns of light across a star. The loop breaches the photosphere at 2 points, its foot points creating regions where the magnetic field lines emerge vertically. These foot points form the seeds of sunspots, darkening as hotter plasma is pushed aside and convection becomes suppressed. For now, the darkening is slight, just a soft dimming in the bright field. The spots will grow later as magnetic flux continues to rise. Only took the quiet emergence of a loop to begin shaping the dark geometry to come. The narrator drifts along one of these emerging magnetic arcs. The plasma surrounding it glows softly, shaped by the lines that guide charged particles along curved paths. In coronagraph images, these loops appear illuminated by hot plasma. Here, the narrator senses their presence as gentle curves of tension. These lines confine plasma trapping heat and is shaping structures that can persist for days or weeks. Their patience contrasts with the chaotic churning beneath them. Only took the sun's hidden architecture to impose order on a sea of moving light. A modern analogy settles softly. These loops resemble iron filings aligning around a bar magnet, though vastly more dynamic and shaped by forces far more complex than simple magnetism. The sun's loops shift and reconnect, constantly responding to unseen changes in subsurface fields. As the narrator moves farther along the arc, small brightness variations within the corona hint at slow flows of plasma, moving along the magnetic lines guided not by gravity but by electric currents. Only took the gentle drift of charged particles to give shape to the sun's hottest region. Yet another scientific uncertainty lingers in this upper region. The mechanism responsible for heating the corona to millions of degrees far hotter than the surface below remains unresolved. Some theories propose nanoflares, tiny magnetic reconnections occurring constantly. Others point to wave heating, where alpha waves carry energy upward. No single model fully explains the observed temperatures. Only took the sun's most basic structure to create one of astrophysics' longest-standing puzzles. The narrator lingers on this mystery, letting it settle quietly among the loops. The corona glows with heat that defies expectation, yet nothing in the present scene feels heated or urgent. Everything remains slow, calm, drifting. Even the processes that will one day give rise to solar storms unfold with patience. As the narrator pulls back, a broad view of the active region emerges. Magnetic loops arch upward and downward, forming a quiet cage of curved tension. Some connect footpoints far apart, forming extended arcs. Others rise only briefly before falling back. Each loop reflects the organization imposed by the underlying fields. Over hours and days, these fields will twist further, storing energy that may one day release. But for now, the region remains serene. Only took the slow accumulation of magnetic tension to prepare for moments that unfold in seconds. As the narrator moves across the surface again, the Sun reveals its polar fields simpler, quieter, more stable than those near the equator. These large-scale dipolar fields reverse every approximately 11 years, marking the solar cycle that shapes long-term activity. The reversal process remains partly mysterious. Scientists understand the broad mechanism but cannot predict its timing with perfect precision. It unfolds over years, guided by the deep dynamo. Only took the slow heartbeat of an 11-year cycle to shape centuries of space weather. Across the surface, the granules continue their bright shimmer, unaware of the twisting forces rising beneath them. Magnetic loops from earlier cycles fade, reconnect, and dissolve, releasing energy quietly in the background. The Sun, often imagined as constant, holds within it a rhythm of hidden transformations. Only took standing far enough away for change to look like permanence. The narrator drifts once more above the emerging active region, noticing the footpoints darkening as the magnetic flux continues to rise. What begins as faint dimming will soon grow into complex sunspots, yet the process remains slow, almost gentle. There is no sudden burst, no sharp transition, only the steady movement of fields through plasma. And in this patient rise lies the first quiet sign of the Carrington Event's precursor, the invisible weaving of magnetic fields into a structure that will one day unravel, with a brilliance brighter than anything Earth's skies have seen in centuries. But for now, the Sun remains in its slow, steady dance of fields, loops, and convection, preparing through calm for a transformation still hidden in the future. The narration drifts softly above the Sun's bright surface, where the churning granules and rising magnetic loops gradually give way to a darker geometry, forming in quiet contrast. The guiding sensation becomes the slow emergence of a sunspot's shadow, a place where the surface cools slightly, where convection weakens and where the Sun's hidden magnetic forces reveal themselves, not through brilliance, but through absence. The scientific fact anchoring this moment is simple. Sunspots appear darker because their strong magnetic fields suppress convection, reducing the upward transport of heat. Their temperatures remain thousands of degrees, yet they look dim against the surrounding radiance. Only took the Sun cooling by a few thousand degrees to create a shadow large enough to swallow a planet. The narrator hovers over a region where 2 footpoints of a rising magnetic loop have strengthened. The granules surrounding them stretch into elongated shapes, their typical patterns distorted by magnetic tension. Slowly, the first hints of darkness appear, not sudden, not sharp, but like ink seeping into bright cloth. These dim patches mark the umbra, the core of the sunspot wrapped by a lighter penumbra, where radial filaments stretch outward like soft spokes. A poetic detail settles here. The filaments of the penumbra resemble delicate strands, each one an outward-flowing structure shaped by magnetic inclination. In high-resolution images, they appear almost like brush textures, faint ridges in a luminous sea. Up close in narration, they feel like quiet signatures of magnetic presence lines that reveal the invisible. Only took a fold-in magnetic fabric to draw patterns across a star's surface. The sunspot grows slowly, fed by continuous flux rising from beneath. The narrator senses its expansion over hours and days, a darkening that spreads like a slow tide. Sunspots often form in pairs, their polarities opposite, linked by buried magnetic fields. Here the pair grows steadily, the umbrae deepening to near black against the photosphere. Only took 2 points of magnetic emergence to create a structure larger than any terrestrial continent. Yet a quiet scientific uncertainty lingers. Why do some sunspots grow enormous while others fade quickly? Models explain magnetic emergence broadly, but the detailed stability of spots, their longevity, structure decay remains partly unresolved. Helioseismic probes offer hints, but the precise geometry beneath the surface eludes direct measurement. Only took the depth of the sun's opacity to keep the life cycle of sunspots partly hidden. The narrator drifts closer to one of the new umbrae. Its darkness is not emptiness, but the glow of cooler plasma trapped beneath magnetic arches. The surface here swirls gently with oscillations. 5-minute waves ripple across the umbra, subtle pulsations caused by acoustic energy from below. These waves produce faint motions detectable only with precision instruments, yet here they feel like the quiet breathing of a darkened patch of star. Only took waves older than any mountain to make a shadow pulse with ancient rhythm. The penumbra stretches outward in fine radial patterns. Its filaments host the evershed flow, a gentle, outward-moving current of plasma that glides along magnetic field lines at a speed of about 1 to 2 kilometers per second. To a star, that flow is modest. To a human, it would be a furious wind. But here, under narration's slow gaze, it becomes an almost meditative drift, a reminder that even the sun's more dynamic processes unfold with patient consistency. Only took a steady outward flow to turn the penumbra into a quiet river of light. The narrator rises to take in the entire active region. Sunspot groups form patterns that evolve over days. In this moment, the region appears calm, though its magnetic complexity grows beneath the surface. The spots drift across the photosphere due to differential rotation. Sunspots near the equator rotate faster than those toward the poles. Over time, their positions shift, subtly stretching field lines and increasing magnetic shear. Only took the sun turning unevenly to twist magnetic fields into intricate knots. This shear stores energy in the corona above, where loops expand and intertwine. For now, the loops remain stable, glowing faintly with trapped plasma heated to millions of degrees. But as the underlying field becomes more tangled, tension accumulates in ways invisible from the surface alone. In certain formations, especially those with complex polarities, this shear can prime a region for eruption. The Carrington sunspot group of 1859, though not visible in this narration, once grew rapidly with such complexity. Here its precursor begins with shadows forming in perfect quiet. Only took a slow build-up in magnetic tension to prepare a flare that would outshine every other in recorded history. The narrator glides across the active region again, observing how convection adapts to magnetic presence. Around sunspots, the granules grow smaller and less vigorous. The magnetic fields inhibit motion, forcing heat to escape around the edges. This creates bright motes, surrounding the spots where convection flows outward in a ring. These motes appear like slow streams guiding plasma away. Only took magnetic obstruction to reshape currents that have existed since the sun's birth. Further out, the surface resumes its bright shimmer. But even there, magnetic traces linger in the form of faculae, bright patches more visible near the limb of the sun. These faculae accompany sunspots, often offset slightly from the dark cores. They contribute more to solar brightness than sunspots subtract. The paradox is gentle but real. The sun can become slightly brighter during periods of high sunspot activity. Only took a few dark shadows to make the sunshine a bit stronger. The narrator lingers on this delicate contrast. The dark umbra appears quiet, cool and stable. The bright faculae shimmer with subtle vigour. Magnetic fields shape both, yet in opposite ways, suppressing convection in one place, enhancing bright contrasts in another. This quiet duality reveals the sun's intricate balance, where light and shadow emerge from the same underlying forces. Only took magnetic fields twisting beneath the surface to paint the photosphere with contrasts. The narrator rises into a broader view where the active region spans a large portion of the solar disk. Around it, the surface transitions from bright granules to dark cores and back again. The active region rotates slowly across the sun's face, carried by the star's vast turning. As it moves, its appearance shifts subtly, foreshadowing the deeper disturbances it may eventually unleash. Yet in this moment, everything remains calm. Light flows outward. Magnetic fields arch gently, and the sunspots rest in their quiet geometry. Only took a star's slow turn to carry a storm across its surface without any visible urgency. And so the narrator remains suspended above the dark and light patterns of this evolving region, sensing how the sun stores energy with immense patience, organising its hidden forces into loops and shadows that will one day shape the space beyond. For now, the formation of sunspots marks only the beginning, dark shapes blooming quietly on a star whose calm is never as simple as it seems. The narration drifts above the growing sunspot group, sensing not the darkness itself, but the tension rising beneath it, slow, quiet, and invisible. The guiding sensation becomes the build-up no eye can see, the gradual strengthening of magnetic shear inside the sun's atmosphere. Nothing dramatic appears at the surface. The granules shimmer as they always do. The penumbrae maintain their delicate filaments. The umbrae sit in patient stillness. Yet beneath these calm shapes, magnetic fields continue to twist, stretch, and braid with a steadiness that reveals how the sun prepares its most powerful events without any outward urgency. The scientific fact anchoring this moment is that solar flares and coronal mass ejections originate not from sudden impulses, but from long-term accumulation of magnetic stress in the corona. Only took days of quiet tension to prepare a flare that releases in minutes. The narrator drifts higher above the active region, until the photosphere blurs into a soft field of brightness. In the chromosphere, spicules rise like thin, flickering strands, jets of plasma reaching thousands of kilometers upward. They appear and vanish in seconds, yet their constant motion hints at the restless fields beneath them. Magnetic lines guide these spicules, shaping their fleeting arcs. Only took a tangle of invisible fields to lift thin flames of plasma into the quiet sky. The view continues into the corona, where magnetic loops extend gracefully, arching high above the surface. These loops glow faintly with plasma heated to millions of degrees, held in place by the complex magnetic structures below. To the narrator, they feel like luminous bridges, quiet, suspended and steady. But their stability hides subtle distortions. Differential rotation continues to twist the loops. Emerging flux presses upward from the convection zone. Neighbouring loops interact through delicate magnetic tension. Only took a smaller symmetry and buried forces to tilt a loop out of its calm alignment. Yet a scientific uncertainty lingers here. Although researchers understand the broad processes that cause magnetic shear, they cannot predict precisely when or where a flare will erupt. The equations governing magnetohydrodynamics remain too complex, and the sun's magnetic environment too intricate to allow exact forecasting. Only took the complexity of plasma physics to keep the timing of storms unknowable. The narrator glides along the top of a long magnetic loop. The field line curves like a soft arc, guiding streams of charged particles that drift gently along it. At times, bright knots appear regions where plasma becomes slightly denser, creating subtle brightness enhancements known as coronal bright points. They appear and fade without sound, yet they reveal shifts in the magnetic architecture, hints of fields reconnecting beneath the surface. Only took a tiny brightening to signal changes too subtle for any eye to follow completely. Beneath these lofty arcs, the active region's core grows increasingly complex. Magnetograms, if one could see them in this narrative, would reveal polarities shifting, mingling, pressing against each other. Opposite magnetic polarities sit close together, forming delta configurations, the most flare-productive kind. But no instrument is present here, only the narrator's quiet drift above the patterns, sensing the slow accumulation of stress. Only took two opposite polarities brushing past each other to build tension that spans thousands of kilometers. The energy stored in these fields increases as magnetic footpoints migrate. Convection tugs gently at them. Differential rotation stretches them sideways. The meridional flow nudges them toward new latitudes. Every movement contributes to the slow winding of magnetic tension. Yet on the surface, nothing dramatic occurs. The brightness remains steady. The granules shift rhythmically. the sunspots drift with measured pace across the photosphere. Only took a star-sized coil of magnetic rope to hold energy millions of times stronger than a volcanic eruption. A poetic detail emerges as the narrator looks down at the penumbra. Faint fibrils lie in delicate streams arranged radially like soft brush strokes. Each strand represents plasma following magnetic inclination. These quiet patterns betray the enormous forces beneath them. Even the smallest motions here are shaped by the invisible tension rising in the field. Only took a pattern of fine filaments to hint at a storm still gathering in silence. Higher in the coronal loops swell slightly bulging, as the internal stress seeks release. The swelling is subtle. Such loops can expand for hours before flaring. They brighten faintly, a quiet glow spread across their curved surfaces. Scientists call these changes pre-flare signatures, though they remain difficult to use predictively. The precision needed to distinguish harmless swelling from imminent eruption remains out of reach. Only took a glowing arc to challenge centuries of understanding. The narrator continues floating above the active region, observing how the deeper layers influence the corona through gradual cumulative processes. Magnetic reconnection, the sudden breaking and rejoining of field lines, has not yet begun. Instead, the corona holds its shape, bending inward from the accumulating stress. The loops twist, fold, and elongate. Some lean toward each other, forming X-shaped configurations. Others fan outward, forming broad cusp-shaped fields. These shapes represent the late stages of magnetic loading. Only took a star's slow heartbeat to push loops into positions one step from release. Yet the exact moment of release remains uncertain. Scientists understand that when magnetic fields become too twisted, they store more energy than their configuration can maintain. They seek lower energy states, but the transition, the sudden restructuring into simpler shapes, requires reconnection. The trigger for that reconnection remains one of the sun's quiet mysteries. Only took the sun's simplest physics to hide the trigger for its most powerful events. The narrator drifts downward again, closer to the photosphere. The sunspot group now spans a region large enough to dwarf Earth. Its umbrae deepen, its penumbrae refine their patterns. What invisible light appears like shadow is in truth a complex interplay between plasma and magnetic force. These dark regions represent the visible signs of suppressed convection. The convection cells around them cluster closer, forming bright boundaries where heat escapes more freely. Only took a bit of magnetic pressure to rearrange the flow of heat across continents of plasma. The granules near the sunspots flicker slightly faster, their lifetime shortened by the magnetic environment. Some split before finishing their typical cycle. Others merge more quickly. These subtle changes offer hints of the deeper tension that continues to rise. Only took a shift in brightness patterns to whisper that a storm lies beneath a calm surface. At last, the narrator rises once more into the high corona. The loops glow brighter than before, filled with hotter plasma. Their edges sharpen, their curvature tightens. All signs suggest that magnetic tension has approached a critical threshold. Yet the sun remains serenely bright, offering no outward sign of the immense energy preparing to break free. Only took hours of subtle distortion to set the stage for a release that will unfold in seconds. The narrator floats in stillness as the active region rests between quiet preparation and sudden transformation. Everything remains calm, though nothing remains unchanged. The sun holds its breath in its own slow, star-sized way, building energy invisibly in its bright and shadowed regions. Soon the loops will reach their limit, and the tension that has risen in perfect silence will spill outward as a flare. But in this moment the sun remains patient, gathering its forces in light and shadow, preparing for brilliance still hidden behind calm. The narration drifts high above the bright arcs of the corona, suspended in the stillness that precedes transformation. The guiding sensation becomes the sudden unraveling of light, the moment when magnetic tension that has gathered quietly for days releases its stored energy in a burst that crosses space faster than anything else the sun can produce. It happens not with a visible warning, not with a gradual shift, but with the swiftness of electric potential overcoming its last restraint. The scientific fact grounding this section is that a solar flare releases electromagnetic radiation almost instantaneously, travelling at the speed of light, reaching Earth in just over 8 minutes. Only took days of quiet magnetic twisting to create a flash that crosses 93 million miles in the time it takes to breathe. The narrator hovers at the edge of the active region as magnetic reconnection begins. It happens when twisted field lines snap and realign into a lower energy state, releasing immense amounts of energy as photons across the electromagnetic spectrum. X-rays, ultraviolet light and visible light surge outward, fanning across the corona. The flare expands like a bloom of brilliance, though in narration it feels less like an explosion and more like a sudden widening of radiance and opening rather than a blast. Only took a shift in geometry to light up a region larger than any storm on Earth. A poetic detail settles in the sudden glow the flare illuminates plasma suspended in the corona, creating bright ribbons that trace the paths of reconnected magnetic lines. These ribbons flash briefly, glowing with the same energy that once lay hidden in the tangle beneath them. In the moments after reconnection, the corona pulses with waves, alphin waves, and magnetoacoustic waves ripple outward, carrying signatures of the energy released. Only took a pulse through plasma to send waves across millions of kilometers of space. The narrator glides closer as the flare's chromospheric footpoints brighten intensely, forming kernels of dazzling emission. These footpoints mark where accelerated electrons crash into denser plasma, heating it rapidly. The heated plasma expands upward, filling newly formed loops in a process called chromospheric evaporation. Though the term evokes heat and motion, it unfolds here in slow grace plasma, rising like the warm breath of a star. Only took a moment of intense heating to push entire loops into new brilliance. Yet a quiet scientific uncertainty lingers. No model fully captures the precise details of magnetic reconnection in the Sun's corona. Simulations replicate aspects of the process, but the exact structure of the reconnecting region, the triggers for instability, and the distribution of accelerated particles remain unresolved. Only took the smaller scales in the universe to keep the largest electromagnetic events partly mysterious. The narrator watches as the flare begins to decay. Its peak brightness fades gradually, though the energy continues to radiate across the heliosphere. High-energy photons race outward unaffected by the solar wind or magnetic fields, carrying the imprint of the flare's brief moment of release. In space, satellites sense the radiation within minutes. On Earth, the ionosphere responds almost instantly, its upper layers swelling with sudden ionization. But these effects lie far ahead. For now, the flare remains an event contained within the Sun's atmosphere. Only took a few minutes of sudden brightness to rewrite conditions across a planet's upper air. Farther above, the corona expands outward, shaped by the flare's energy. Regions once faint become sharply illuminated. Plasma flows along loops, creating bright post-flare arcades that rise and broaden slowly. These arcades are like scaffolds of cooling plasma, revealing the geometry of the reconnection region long after the brightest flashes passed. Their slow ascent marks the dissipation of stored energy. Only took hours of cooling to reveal a pattern formed in seconds. The narrator drifts around the active region, observing the flare's aftermath. Some loops remain intact, others reconfigure entirely. The corona above the sunspot group becomes filled with soft light glowing in ultraviolet and X-rays. These emissions continue long after the peak, providing clues about temperature density and the rate of energy release. Yet even as this scene unfolds, something else stirs in the lower corona, a shifting bulge, a swelling arc, a faint outline forming against the bright background. Only took the flare's release to warn that a deeper transformation may follow. That transformation is the birth of a coronal mass ejection, though here it begins only as a subtle expansion. The flare alone would already be a significant event, but magnetic reconnection also reconfigures large-scale structures, sometimes freeing an entire magnetic flux rope. The narrator senses this slow emergence a vast arching structure begins to rise, its edges brightening. But the CME is still forming in this moment, and the flare remains the central focus. Only took the sun's rearrangement of fields to prepare a cloud of plasma, hundreds of billions of tons in mass. A poetic image arises in the flare's coronal shock wave, an expanding ring of disturbance that travels outward like a ripple in quiet water. In extreme ultraviolet images, it appears as a faint arc moving across the corona. In this narrative, it feels like a soft breath, an outward exhalation from a star. It sweeps across nearby regions, compressing plasma momentarily before fading. Only took a flash of energy to set the corona trembling like a field touched by wind. Yet another scientific uncertainty lives here. Although flare-induced shockwaves are well documented, their exact interaction with the corona and solar wind remains complex. Some shockwaves trigger additional reconnection, others dissipate quickly. Their effects depend on coronal density field geometry and the underlying disturbance. Only took one disturbance to create outcomes that vary across hidden conditions. As the narrator drifts higher, the flare's full extent becomes clear. Its loops rise thousands of kilometers. Its ribbons stretch across tens of thousands more. The entire region glows with transient brightness. But gradually, as minutes pass, the intensity fades. The loops cool, the ribbons dim, the post-flare arcades settle into their graceful equilibrium. Only took a star's quiet cooling to return a region from brilliance to calm. Below the sunspots remain unchanged in their geometry. They do not brighten or flare themselves. Their darkness endures unaffected by the radiative outburst above. They serve as anchors, silent reminders that the energy released came not from motion, but from magnetic tension. Only took the quiet of a shadow to hide the power of an eruption. And so, as the flare subsides, the narration hovers between quiet aftermath and the slow rise of deeper forces. The sun has released part of its stored energy, yet another transformation is underway. The CME forming below builds outward momentum, preparing to detach fully. The flare has already illuminated space with its sudden radiance. Soon the sun will send matter outward as well. The narrator remains suspended above the bright and dark interplay, watching the flare's light drift outward into space where nothing can slow it, while the deeper forces of the corona prepare to lift an enormous mass of plasma into motion. For now, the flare rests in its cooling afterglow, its energy dispersing into space with calm persistence. But the sun, having unbound its magnetic knots, is not finished. The unravelling has only begun. The narration rises slowly into the bright stillness left in the flare's wake, drifting just above the arching loops that continue to glow with lingering heat. Here, suspended in the upper corona, the guiding sensation becomes plasma freed into open space. The sun has already released its burst of light. Now it releases matter itself, caught in a vast magnetic structure that begins to lift away from the star with a patience that feels almost contradictory to its scale. The scientific fact anchoring this moment is that coronal mass ejections eject billions of tons of charged particles, electrons, protons, and ionized atoms into the heliosphere, often travelling at hundreds to thousands of kilometers per second once fully accelerated. Only took a single moment of reconnection to free a cloud large enough to swallow worlds. At first, the narrator senses only subtle changes, bright arcs swelling higher, magnetic loops stretching as if pulled from within. Beneath them, the sunspot group remains steady, its dark geometry unchanged. But above a dome-shaped structure forms known as a flux rope, a twisted bundle of magnetic field lines filled with plasma. Its shape grows slowly, expanding upward like a luminous balloon of charged particles. Only took the quiet tension of buried fields to sculpt a structure taller than mountains stacked end to end. A poetic detail emerges as the flux rope brightens along its edges. These bright rims mark the boundaries where magnetic fields reconnect and accelerate particles. In extreme ultraviolet light, such structures reveal themselves as glowing bubbles against the corona. But in narration, They feel like slow rising lanterns, vast, weightless and serene despite their power. Only took a gentle upward swell to lift a storm into the sky of a star. Below the flux rope, a dark cavity opens as plasma flows upward. Coronagraph images later show these cavities as void-like spaces within the corona shaped by low-density regions formed during CME liftoff. The narrator senses this cavity as a hollow silence, an emptiness carved by motion so enormous it becomes calm. Only took the removal of a little plasma to create a darkness large enough for a star to feel. Yet a quiet scientific uncertainty lingers the precise trigger that transforms slow magnetic swelling into a CME remains debated. Some models emphasize tether-cutting reconnection. Others propose the torus instability, where the magnetic conditions above the rope weaken enough to let it rise freely. No single explanation covers every event. Only took the universe refusing simplicity to make even a star's storms multifaceted mysteries. The narrator watches as the CME gains momentum. Its initial rise is slow, perhaps tens of kilometers per second, barely perceptible against the vastness, but acceleration soon follows. As magnetic energy releases, the structure pushes outward more forcefully. The corona stretches around it, forming a smooth leading edge. Behind it, the cavity expands. At the base, bright flare ribbons separate slowly as reconnection continues. Only took the sun rearranging its fields to push a billion-ton cloud into flight. Above the rising structure, the solar wind carries faint streams of plasma outward. The CME encounters this background wind almost immediately shaping its outer layers into a broader front. Shock waves develop ahead of it if the CME moves faster than the surrounding solar wind waves that will eventually influence particle acceleration near Earth. But for now, these shocks remain faint, forming only a soft suggestion around the expanding sphere. Only took a bit of extra speed to send a ripple through interplanetary space. The narrator glides closer to the CME's outer boundary. It is not a solid wall, but a thin shell of compressed plasma shaped by the magnetic field lines that stretch outward with it. Within the CME, the magnetic field rotates smoothly, following the flux rope structure. Outside, the sun's background field presses against it. This interplay defines the CME's future interactions with planets and spacecraft. Only took a twist in magnetic direction to determine whether a planet's field will shield or yield. A subtle irony settles here. The CME appears peaceful, its rise graceful, its expansion slow compared to flares. Yet it carries far more mass and in many cases far more long-term influence. While flares send light, CMEs send matter that can alter magnetospheres, currents, and atmospheric chemistry when it arrives. Only took a cloud of plasma drifting outward to shape the future of space weather on distant worlds. The narrator drifts above the flux rope, watching its shape broaden as it escapes the tight influence of the solar corona. Once above a certain altitude, often around 2 solar radii, the CME becomes largely independent of the sun's magnetic confinement. It now follows the path shaped by the heliospheric magnetic field in the solar wind. The acceleration phase peaks. Beyond this point, the CME coasts outward with near constant velocity. Only took a few 100,000 kilometers to transform a rising arc into a free-floating storm. Beneath the CME, the sun continues its quiet reconfiguration. Magnetic fields settle into new positions. Post-flare loops cool, gradually arching like glowing ribs of a star. The chromosphere quiets. The brightness of the flare decays. At the surface, sunspots persist their geometry unchanged. They act as silent anchors for the activity that has already unfolded above them. Only took the stillness of 2 dark spots to outlast the storm they triggered. As the narrator pulls back, the full scale of the CME becomes clear. It spans millions of kilometers, its spherical boundary expanding outward, like the slow bloom of a flower made of charged light. The sun rotates beneath it, indifferent to the cloud drifting away. Though the CME originated from a specific region, it will soon lose all ties to its birthplace. The heliosphere becomes its environment now. Only took a shift of perspective to make a continent-sized shadow seem small against a star-sized sky. Yet another scientific uncertainty remains. Predicting CME trajectories remains difficult. While models track initial directions, interplanetary conditions alter paths through deflection, rotation, and deformation. Some CMEs merge with others. Some dissipate faster than expected. Some maintain coherence for astronomical units. Only took a little turbulence in the solar wind to hide a storm's long-distance intent. As the CME drifts outward, the narrator senses its internal rotation, magnetic helicity preserving the structure of the flux rope. That rotation may determine the storm's geo-effectiveness if it reaches Earth. If the CME's magnetic field is oriented southward, relative to Earth's own field reconnection becomes easier, allowing the storm to inject energy into the magnetosphere. If oriented northward, much of its impact is deflected. Only took a field aligned one way to shape a planet's auroras. Aligned the other way, and the storm slides harmlessly past. The narration lingers on the trailing edge of the CME as it leaves the corona entirely. Behind it, the sun's atmosphere begins to refill the evacuated region. Plasma flows inward, slowly healing the transient wound left by the departing cloud. The corona resumes its brightness. Spicules rise and fall. The solar wind continues. The star regains its calm. Only took a few hours for a star to recover from releasing a storm with the mass of mountains. From this high vantage, the narrator sees the CME as a faint widening halo drifting into interplanetary space. Soon, it will enter the solar wind's flow channels shaped by rotating magnetic sectors that spiral outward with the sun's spin. It will follow those pathways, quietly expanding, cooling, and carrying within it the magnetic memory of the region that launched it. Only took the sun's rotation to carve invisible highways for storms to follow. And so the narrator watches the cloud drift onward, slow, massive, and serene. The sun's atmosphere settles beneath it, preparing for the next cycle of emergence, build-up, and release. The flare has faded, the CME has lifted, and now the storm begins its long journey across the heliosphere, where Earth rotates quietly in its path, unaware of the slow-moving cloud that has just begun to cross 93 million miles of space. The narration drifts outward with the rising cloud of plasma watching, as the coronal mass ejection enters the wide, slow-moving river of charged particles that constantly flows from the sun. Here the guiding sensation becomes the long passage across the solar wind's highway, a region where the sun's breath fills all space, where streams of particles move outward in spiraling patterns shaped by rotation pressure and magnetic fields. The scientific fact anchoring this moment is clear: the solar wind, composed largely of electrons and protons, flows continuously, at speeds ranging from roughly 300 to 800 kilometers per second, creating the vast heliosphere through which every CME must travel. Only took the sun's steady outflow to build a sphere larger than the orbit of any planet. As the narrator drifts alongside the CME, the solar wind reveals itself not as empty flow, but as a textured shifting medium. It holds regions of higher and lower density pockets of turbulence and long channels defined by the sun's magnetic polarity. Because the sun rotates, these channels form spirals, Parker spirals winding outward across billions of kilometers. The CME now enters one of these spirals, its leading edge interacting with the wind around it. Only took a slow turn of a star to twist the solar wind into a galaxy-sized braid. A poetic detail emerges in the faint shimmer of charged particles drifting in the CME's wake. These particles scatter sunlight slightly, creating a soft, ghost-like glow, detectable in coronagraph images. In narration, this glow feels like dust drifting across a quiet field, visible only when caught at just the right angle. It marks the path the CME follows, a path shaped not by straight lines, but by curves and spirals. Only took a little scattered light to trace a storm's wandering through space. Yet a quiet scientific uncertainty lingers. The structure of the solar wind remains complex and only partially predictable. In situ measurements from spacecraft reveal fluctuations, shocks and tangles that cannot be seen from afar. These hidden structures significantly affect how CMEs evolve, merge and accelerate. Only took the complexity of space between planets to obscure the true conditions a storm will face. The narrator watches as the CME begins to stretch. In the vacuum of interplanetary space, there is no pressure to contain it. The cloud expands steadily, its interior cooling as it grows. What left the sun as a compact flux rope now becomes a sprawling diffuse region, with boundaries that grow more subtle with distance. Only took a few million kilometers of travel to turn a sharp edge into a soft frontier. The magnetic field inside the CME rotates slowly, preserving its helical shape. Outside, the solar wind flows past, sometimes compressing parts of the CME, sometimes letting it expand freely. These interactions create ripples along the boundary, a delicate dance between two magnetic environments. Only took two fields brushing past each other to write patterns across a storm's invisible skin. As the narrator moves farther from the sun, the solar wind shows regions of contrast. Fast streams from coronal holes, areas of open magnetic field, catch up with slower wind from near the equator. Where they meet, interaction regions form compressed zones with enhanced magnetic fields and density. If the CME enters such a region, it may accelerate or distort. In other areas, the solar wind thins, offering less resistance. Only took a difference in wind speed to turn a smooth ride into a shifting journey. A modern analogy settles gently. The CME travelling through the solar wind resembles a drifting balloon caught in jet streams, pushed, stretched and steered by currents it cannot control. The solar wind is calm on average, but full of subtle forces, each one capable of altering the storm's path. Only took the faintest current to nudge a billion-ton cloud. The narrator senses as the CME begins to drive a shockwave ahead of it. If the CME moves faster than the background solar wind, its leading edge compresses the plasma in front. The shock steepens, accelerating particles to high energies. These particles, known as solar energetic particles, race ahead of the CME, reaching Earth long before the cloud itself. Only took a shockwave in thin plasma to send particles across space at near relativistic speeds. Yet not all aspects of this shock are well understood. Scientists know the general mechanism, but cannot predict exactly which events will produce strong particle acceleration. The distribution of turbulence and magnetic irregularities plays a role, but these details remain difficult to measure. Only took the hidden roughness of space to make predictions uncertain. The narrator continues drifting beside the cloud as it moves into regions where the solar wind begins to align more strongly with the Parker spiral. The CME's motion becomes increasingly guided by the sun's large-scale magnetic field. This alignment influences how the storm will eventually interact with planetary fields. If its internal magnetic orientation remains steady, it will approach Earth with that original structure. If it rotates or becomes distorted en route, its effects may differ dramatically. Only took a twist during transit to change the fate of an entire magnetosphere. Farther outward, the CME passes the orbit of Mercury. Here the solar wind is still dense enough to shape the cloud strongly. A portion of the storm's outer layers brush against the fast-moving planetary plasma environment. Mercury possesses only a small magnetosphere, offering little resistance. If this were a direct encounter, the interaction would be intense, but the CME travels slightly off-angle, barely sensing the planet's presence. It continues outward. Only took a shift of a few degrees to let one world escape notice. As the CME nears the orbit of Venus, its expansion slows slightly. Venus lacks a magnetic field, relying on its ionosphere to deflect solar wind. A large CME can compress that ionosphere, dramatically stripping particles from the upper atmosphere. But again, in this quiet retelling, Venus lies off to the side. The cloud's path remains unchanged. Only took a small miss to leave a planet's atmosphere untroubled. The solar wind grows thinner as the cloud approaches Earth's orbit. Stream interactions become clearer, turbulence sharpens. Here the heliosphere feels more structured, shaped by planetary magnetic fields, solar rotation, and the long spiraling threads of the solar wind. The CME slows slightly at speed moderated by drag from the background plasma. Only took the faint drag of distant particles to slow a storm that began with the force of a star. As the narrator drifts forward with the cloud, Earth appears ahead not dramatically, not with tension, but as a small, pale sphere moving silently through its orbit. The planet's magnetic field extends outward in a teardrop shape, forming a buffer against the solar wind. The CME approaches this magnetosphere like a slow tide moving toward a quiet shore. Whether the interaction becomes powerful or gentle will depend on magnetic alignment, something still unknown. Only took the angle of a field line to determine how deeply a star's outflow will seep into a planet's shield. In this moment, the CME has not yet touched Earth. It drifts in the solar wind, expanding, cooling, and carrying with it the memory of the active region that launched it. Behind it, the sun glows quietly, already preparing new cycles of emergence and calm. Ahead, Earth rotates with steady patience, unaware of the cloud approaching across millions of kilometers of space. And so the narrator remains suspended at this threshold, drifting with the storm as it prepares to meet the next boundary in its long, slow journey. The narration drifts closer to Earth, now watching as the expanding cloud of solar plasma approaches the invisible barrier that surrounds the planet. Here, the guiding sensation becomes Earth slowly turning into the path of the arriving disturbance. Nothing dramatic happens at first because the encounter unfolds on scales too large for suddenness. Earth keeps rotating through day and night. Cloud systems continue their quiet wandering, and the magnetosphere holds its teardrop shape in the solar wind. Yet ahead of the CME's leading edge, the magnetic field lines of the planet begin to tremble slightly as charged particles push against them. The scientific fact grounding this moment is simple. Earth's magnetosphere forms a protective cavity in the solar wind, its shape determined by the balance between magnetic pressure and the flow of charged particles streaming from the sun. Only took a planet's magnetic whisper to hold back a wind that fills space. As the CME draws closer, its shock wave reaches the magnetosphere first. This shock compresses the dayside boundary, the magnetopause pushing it inward by tens of thousands of kilometers. Satellites that normally orbit safely within the magnetosphere may briefly find themselves outside, exposed directly to the solar wind. Only took a momentary press of plasma to squeeze a planetary shield smaller than usual. A poetic detail emerges as the narrator senses the bow shock ahead of Earth. This shock forms where the solar wind slows abruptly upon encountering the magnetosphere. It resembles a quiet wave that forms before the hull of a boat, not loud, not bright, but definite. In this retelling, it feels like a soft ripple in the darkness, marking the meeting point of two enormous flows, the solar wind outward and the magnetosphere resisting inward. Only took a faint wave to signal the start of a planetary encounter, yet a scientific uncertainty lingers. How precisely the magnetosphere responds depends on the CME's magnetic orientation, a detail unpredictable until the storm arrives. If the CME's field points northward, it aligns gently with Earth's field, causing minimal disturbance. If it points southward, it opposes Earth's field, allowing reconnection to open pathways for solar plasma to enter the magnetosphere. Only took a flip in polarity to transform a quiet encounter into a geomagnetic storm. As the CME's magnetic front reaches the magnetosphere, Earth's field lines begin to strain under the pressure. The magnetopause is pushed inward to perhaps 6 Earth radii on the day side. Under ordinary solar wind conditions, it rests around 10. This compression changes the entire geometry of Earth's magnetic bubble. Particles trapped in the outer radiation belt become energized, and some drift inward or outward. The plasma sphere, a region of cold, dense plasma surrounding Earth, begins to erode at its outer edges. Only took a little extra pressure to reshape layers of a planet's invisible architecture. The narrator glides around the sunlit side of Earth, seeing the magnetopause ripple gently like a curtain pressed by a slow-moving tide. The CME continues pushing outward against the solar wind behind it, and Earth continues drifting quietly through its orbit. No human eyes witness this interaction directly. It unfolds far above the atmosphere, silent and vast. Only took the right perspective to see calm in an event that spans millions of kilometers. Behind Earth, the magneto-tail stretches away into the night side, elongating under the pressure. This tail, composed of two lobes of magnetic field lines, separated by a thin current sheet, holds the potential for its own transformations. As the CME compresses the day side, the night side stores energy like a distant reservoir. Only took the push of one side of a magnetosphere to prime the other for release. A poetic image emerges as the narrator drifts through the magnetosheath, the region of turbulent plasma between the bow shock and the magnetopores. Here conditions fluctuate rapidly. Magnetic fields twist, densities shift, temperatures vary. The sheath becomes a region of transition carrying signatures of both the solar wind and Earth's magnetic presence. It is a boundary shaped not by lines but by gradients. Only took a zone of turbulence to blur the edge between star and planet. Yet another scientific uncertainty remains. Predicting magnetosheath behavior during strong solar storms is difficult. Turbulence evolves chaotically, and spacecraft measurements reveal variability even across small distances. Numerical simulations approximate these flows but cannot capture every detail. Only took the unpredictability of chaos to keep even the best models partly blind. As the main body of the CME reaches the magnetopores, its magnetic field begins interacting more directly with Earth's. If the CME's field is oriented southward opposite Earth's, the interaction becomes more efficient. Magnetic reconnection occurs along the dayside boundary opening portals, where solar plasma enters the magnetosphere and funnels along field lines toward the poles. Only took two opposing fields touching to allow a star's particles to slip into a planet's shield. The narrator drifts downward along one of these field lines, following the invisible pathway into the upper atmosphere. Charged particles begin precipitating into the ionosphere, colliding with oxygen and nitrogen. But this is only the earlier stage. The full impact of the storm has not yet arrived. Still, the first hints appear: faint softening of Earth's polar atmosphere, subtle shifts in density, and the earliest increases in ionization. Only took a whisper of incoming particles to change the chemistry of a planet's sky. Returning to the dayside boundary, the narrator observes the onset of geomagnetic disturbances. The magnetic field measured at Earth's surface begins to fluctuate subtly as currents in the magnetosphere adjust to the new pressure. These variations, though minor, now foreshadow the deeper disturbances to come. Only took the slightest shift in field strength to signal a storm still gathering momentum. Meanwhile, Earth continues its rotation. Land moves beneath the glow of sunlight, oceans reflect the sky, and the atmosphere circulates without any hint of the vast plasma event unfolding far above. This quiet contrast becomes a soft irony. Surface life remains unchanged, while space becomes troubled by forces thousands of times stronger than any storm on Earth. Only took a thin layer of air and rock to hide cosmic motion from creatures living below. The narrator drifts around to the terminator, the line between night and day, where Earth's magnetic field lines begin to stretch into darkness. Here the magneto-tail continues lengthening, reshaped by the CME's steady pressure. The tail lobes draw farther apart and tension accumulates along the central current sheet. Though the release will come later, the preparation has already begun. Only took the sun's distant push to wind up a tail 200 Earth radii long. Polar cusp regions where Earth's magnetic field lines open slightly become more active as well. The CME increases the flux of particles entering these narrow funnels. Instruments in these regions would record spikes in ion energy. But here in narration, they feel like faint streams of starborn particles brushing lightly against the atmosphere. Only took an open magnetic window to let pieces of the sun graze a planet's sky. The CME continues pressing its momentum, slow but steady. Earth's magnetosphere adjusts continuously, reshaping itself without sound or light. These adjustments will eventually ripple downward into the ionosphere, setting the stage for currents that flow through the atmosphere and even through the ground. But for now, everything remains suspended in a quiet moment of approach, a planet turning gently as a cloud of plasma begins to wrap itself around the magnetic shield that has protected it for billions of years. Only took a few million kilometers of drift to bring a star's breath and a world's field into contact. And so, the narrator pauses in the vastness between Earth and the CME, sensing the slow, inevitable merging of two enormous systems. The storm has reached the threshold of interaction. Soon it will enter fully reshaping fields, currents, and skies. But in this moment, the encounter remains in its quiet beginning. A meeting of star and planet unfolding with a patience measured not in minutes but in space itself. The narration drifts into the space just above Earth's night side, where the magnetotail stretches like a long dark river flowing away from the sun. Here the guiding sensation becomes stored tension, quiet, invisible and immense. The CME has pressed on the dayside magnetosphere, and now the nightside responds in its own slow language. This region unseen from Earth's surface becomes the place where magnetic fields gather the energy passed inward from the solar wind, holding it like a reservoir waiting for release. The scientific fact grounding this moment is that geomagnetic storms unfold not only on the dayside, but also deep within the magnetotail, where reconnection can suddenly occur, sending energy back toward Earth along magnetic field lines. Only took a tug from the sun to coil a tail hundreds of Earth-lengths long with silent tension. As the CME continues pushing, the magnetotail's lobes stretch farther apart. Magnetic field lines drawn taut form long, slender sheets. These sheets guide currents, planet-sized electric channels flowing through near-Earth space. In the central plasma sheet, charged particles become energized, forming hot populations that drift and swirl in patterns shaped by reconnection and turbulence. Only took a distant flare to heat a river of plasma that lies in the planet's shadow. A poetic detail emerges in the faint invisible glow of the plasma sheet, detectable only to instruments yet rich in structure. In this retelling, it feels like the quiet shimmer of heat rising from stone on a cool night, subtle, thin, a whisper of motion without form. Only took a thin band of charged particles to carry the imprint of a star's breath. Yet a scientific uncertainty lingers. Predicting when tail reconnection will occur remains difficult. Scientists understand that magnetic fields stretch too far, eventually break and reconnect, but the precise thresholds, timings and locations remain elusive. Variability in the solar wind, small-scale instabilities and turbulence all play roles that models only approximate. Only took the complexity of plasma to keep a predictable pattern perpetually just out of reach. As the CME's pressure builds, the magnetotail enters a more strained configuration. The current sheet thins. Magnetic fields near the centre weaken as field lines draw taut. The plasma grows hotter with ions and electrons drifting in opposite directions, creating conditions ripe for instability. These instabilities gather quietly like faint tremors that precede a distant shift. Only took the gentlest imbalance to prepare an entire tail for sudden release. The narrator drifts toward the distant region where reconnection often begins somewhere between 15 and 30 Earth radii down the tail. Here, magnetic field lines of opposite direction approach each other, held apart only by a thin layer of plasma. When the conditions align, they snap and merge, releasing energy and accelerating particles both earthward and tailward. The snapping itself is silent, invisible, yet powerful. Only took two field lines meeting in darkness to unleash a surge of energy across near-Earth space. The tail now enters the substorm phase. At first, the reconnection point forms far down the tail. Plasma jets outward in both directions, one toward deep space, the other toward Earth. The earthward jet carries energized particles and compressed magnetic fields. These move faster than the local alpha and speed-producing disturbances that propagate through the tail like faint invisible waves. Only took the release of one knot in the tail to send a pulse racing home. As the narrator follows the earthward jet, the magnetotail begins to collapse inward. Field lines that had stretched for hours snap back toward Earth, pulled by tension forces seeking lower energy configurations. This collapse, A depolarization creates a sudden strengthening of the magnetic field outside Earth. Satellites passing through this region measure sharp changes. Fields intensify, particles accelerate, plasma flows alter direction. Only took a tail relaxing back to its original shape to jolt an entire region of space. A poetic image arises in the depolarization front, a thin boundary that moves earthward like a quiet wave. It marks the transition from stretched tail-like geometry to a more compressed dipole shape. Instruments record it as a jump in magnetic field strength. In narration, it feels like the moment a pulled fabric is released, gentle in motion, yet filled with stored tension. Only took a single moving front to reshape the plasma environment millions of kilometers from Earth. As particles stream earthward along field lines, they spiral into the upper atmosphere, concentrating near the auroral oval. Oxygen atoms glow green, and at higher altitudes red. Nitrogen glows blue and purple, yet here the lights have not yet fully intensified. This is only the beginning of the auroral surge. The main phase awaits the deeper storm still forming. Only took a handful of incoming particles to colour the edges of a silent sky. Meanwhile, the CME continues pressing from the day side. The magnetosphere remains compressed. More reconnection occurs on the sunlit side, funneling additional particles into the magnetotail. These particles join the returning currents, feeding the substorm cycle. The tail grows active, filled with jets waves and sudden changes in flow direction. What appears as stillness from Earth's surface becomes an intricate dance of fields and particles in the darkness behind the planet. Only took a night sky free of visible clues to hide the storm raging above it. A scientific uncertainty lingers gently. The full relationship between storms driven directly by CMEs and those driven by magnetotail reconnection remains complex. CMEs initiate global disturbances, but substorms follow their own rhythm, sometimes aligning and sometimes diverging from the main storm cycle. The interplay remains one of the great puzzles of space weather science. Only took two overlapping processes to blur the boundaries between cause and consequence. The narrator now drifts toward the inner magnetosphere. Here the ring current begins to strengthen. Energetic ions, mostly oxygen, hydrogen and helium, move westward around Earth, forming a drift current that weakens the planet's magnetic field slightly. This weakening will later be recorded on the ground as a drop in the Diest index, a key measure of geomagnetic storm intensity. But for now, the ring current is only beginning to grow. Only took the steady drift of ions to carve a quiet depression into a planet's magnetic field. The plasmasphere, Earth's region of cool, dense plasma, responds slowly to the growing storm. Its outer layers begin to erode, forming a plume that extends sunward. This plume carries cold plasma outward, where it will influence how reconnection proceeds at the dayside magnetopause. In the language of space physics, cold plasma can slow reconnection rates, shaping the storm's unfolding. But visually in narration, the plume appears like a faint invisible mist lifting from a calm lake. Only took a thin layer of cold plasma to shape how a star's breath meets a planet's shield. Farther below in the ionosphere, currents begin to intensify. These currents form in response to electric fields imposed from the magnetosphere. They flow along narrow arcs, interacting with the partially ionized atmosphere. This interaction heats the upper layers, distorting density profiles and affecting communication signals. But from the perspective of the narrator, they resemble soft drifting patterns, electric tides moving through air too thin to feel. Only took a whisper of electric flow to ripple through a sky unseen. As the narrator pulls back, the entire magnetotail becomes visible, stretched, twisted, then collapsing into brighter, more energized configurations. Earth's magnetic field pulses with slow changes. The solar wind continues pressing. The CME's main body wraps itself around the magnetosphere like a vast drifting fabric, shaping currents and fields with steady patience. The storm has begun its true inward journey. Yet the strongest disturbances still lie ahead. The magnetotail has released one store of energy. The The magnetosphere is adjusting. Earth rotates quietly beneath it, unaware of the vast structures shifting in silence above. Only took the turn of a world to hide the cosmic scales moving just beyond its sky. And so, the narrator remains suspended in the nightside shadow, sensing the slow approach of deeper phases, the ring current strengthening auroras preparing to brighten, and the magnetosphere reshaping itself moment by moment. The storm grows inward. Soon its effects will reach the atmosphere itself. But for now, everything lies in a state of patient transition. A world rotating a tail, releasing tension, and a storm continuing its long quiet descent toward the boundaries of air and light. The narration moves inward toward the region where Earth's magnetic field meets the upper atmosphere, drifting into the quiet boundary between space and air. Here, the guiding sensation becomes the slow descent of storm-driven energy into the ionosphere, a place where charged particles reshape invisible structures with calm persistence. The CME continues to press from the day side, the magnetotail continues releasing tension from the night side, and together they guide a steady influx of particles along magnetic field lines toward the polar atmosphere. The scientific fact grounding this moment is that geomagnetic storms drive strong electric currents in the ionosphere, particularly the auroral electrojets, which flow around the polar regions and alter both Earth's magnetic field and the behaviour of the upper atmosphere. Only took the drift of particles from 93 million miles away to send currents flowing across the sky of a planet. As the narrator descends into the polar cap, the upper atmosphere reveals subtle changes. The ionosphere grows denser in some regions and thinner in others. Pockets of increased ionization form where particles enter along open magnetic field lines. In the E and F layers, ionization patterns shift as energetic electrons collide with atmospheric gases. The result is quiet, steady restructuring, no sound, no bright flash, no outward turbulence. Only took invisible collisions to redraw the map of a sky no one sees directly. A poetic detail emerges in the thin glow forming along Earth's high latitudes. At first, this glow lingers faintly like the dim outline of something waiting to take full shape. Most of the auroral energy has not yet arrived. These are merely the first emissaries, the earliest particles spiralling down with enough speed to excite oxygen and nitrogen. Their glow is soft greenish, woven loosely across the horizon. Only took a handful of electrons to whisper the first colours of a storm-lit night. Yet a scientific uncertainty lingers. Predicting the intensity, location or timing of auroral arcs remains challenging. Although models simulate many factors, the chaotic interplay of field-aligned currents, ionospheric conductivity and magnetotail reconnection introduces complexity that defies perfect forecasting. Only took the smallest turbulence in near-Earth space to blur the boundaries of what we can predict. The narrator hovers above the night-side auroral oval. At this stage, the oval begins to expand equatorward, driven by increased convection in the magnetosphere. Electric fields guide plasma across vast distances from dawn to dusk, from the polar cap to the mid-latitudes. These flows reshape the entire ionosphere, drawing arcs, spirals, and diffuse patches of light into motion. Only took the drift of an unseen electric field to shift the glow of a continent-sized curtain. Meanwhile, in the magnetosphere above, field-aligned currents intensify. These currents, Birkeland currents, flow along magnetic field lines between the magnetosphere and ionosphere. They complete giant circuits, forming upward and downward currents that heat the upper atmosphere and create pressure-driven winds. To the narrator, they feel like vast silent waterfalls of charged particles flowing into and out of the sky. Only took a current measured in millions of amperes to move through air so thin it barely counts as atmosphere at all. As the CME's main body wraps more fully around Earth, the pressure on the magnetosphere continues to increase. Reconnection on the day side intensifies, feeding even more plasma into the magnetotail. The tail responds with additional reconnection burst, releasing further pulses of energy toward Earth. Each new pulse triggers fresh waves of particles spiraling into the poles. Slowly the aurora brightens, Only took a cycle of tail and dayside interactions to lift the faint glow into deeper radiance. The narrator moves closer to the region where the auroral electrojets strengthen. These currents flow horizontally through the ionosphere driven by magnetospheric electric fields. Their presence alters Earth's magnetic field at the surface, causing fluctuations detected by ground-based instruments. Power systems, pipelines, and communication networks may feel these effects in coming hours, though none of that yet appears in this silent scene. Only took a sky full of drifting particles to stir currents that later hum through the ground itself. A poetic detail arises in the way auroral arcs begin to ripple. These arcs are not static. They move like quiet waves, their edges curling slightly as new particles arrive. The arcs brighten along their lower boundaries where energetic electrons collide most efficiently with atmospheric oxygen. Green light dominates between roughly 100 and 300 kilometers in altitude. Higher up, rare red emissions appear oxygen atoms excited at lower pressures. Only took a collision in thin air to paint the sky with colours no surface storm could rival. As particles continue to fall along field lines, the ionosphere heats and expands. Atmospheric drag increases slightly at low Earth orbit altitudes. Satellites passing overhead encounter thicker air than usual, altering their paths. But from the narrator's perspective, this expansion feels like a gentle lifting air, rising with quiet warmth, its layers swelling softly beneath the invisible flow of energy. Only took a touch of heat from particles older than a solar flare to nudge the atmosphere outward. Yet another scientific uncertainty remains the detailed coupling between the magnetosphere and ionosphere. During strong storms involves feedback still not fully understood. Electric fields shape currents. Currents heat the atmosphere. Heating changes conductivity. Conductivity alters how fields map downward. The system loops endlessly complex and dynamic. Only took nature's preference for interdependence to make one region's change ripple through all the rest. The narrator moves toward the dawn side of Earth, where the earlier sunlight begins to touch the upper atmosphere. Here the storm's influence interacts with the slow transition from night to day. Ionospheric densities shift more rapidly, and electric fields reorganize as the conducting sunlight re-enters the system. This mixing of storm-driven currents with diurnal cycles creates patterns that drift and swirl unpredictably. Only took the rising sun to add another layer of complexity to a sky already brimming with charged motion. The auroral oval now expands further, reaching mid-latitudes. Its brightness intensifies. Arcs multiply, forming intricate geometries, spirals, bands, rays, curtains that ripple with the precision of field lines. Each structure reveals the flow of energetic electrons guided by Earth's magnetospheric configuration at the moment. Only took the choreography of magnetic fields to turn invisible physics into visible light. Downward, the ionosphere grows more active. Ionization over the poles increases dramatically, creating regions of enhanced density that affect high-frequency radio signals. Communication paths refract, distort, or fade entirely. But in narration, this appears not as disruption, but as a quiet shifting of the sky's transparency, a reminder that storms above alter the pathways of sound and signal below. Only took flashes of auroral electrons to reshape the behavior of waves traveling through the air. Higher still, the magnetosphere continues to adjust. Plasma flows from the magnetotail move inward, forming bursts of energetic particles that drift around Earth. These particles feed the ring current, which grows stronger. The ring current weakens Earth's magnetic field at the surface by small but significant amounts. Ground-based observatories will soon register these drops. But here, drifting at altitude, the narrator feels only a subtle softening of the magnetic environment, a slight relaxation, as though the field's usual firmness becomes more pliable. Only took a belt of drifting ions to ease the strength of a planet's magnetic grip. The atmosphere below responds to heating with quiet winds. Thermospheric winds shift direction, altering the distribution of density at altitudes where satellites orbit. These wind patterns form global circulations changing over minutes and hours. They carry heat from auroral latitudes toward lower latitudes, redistributing energy through an atmosphere too thin to feel yet large enough to matter. Only took a rising of air invisible to humans to transport energy across hemispheres. As the narrator pulls back for a moment, Earth appears wrapped in a shimmering ring of light. The auroral oval pulses, brightening in waves as fresh particle injections arrive from the magnetotail. Lines of light bend along magnetic geometry, forming luminous curtains that stretch hundreds of kilometers high. They drift with calm confidence through the polar night. Only took a star's distant storm to lift a world's dark sky into luminous motion. In this moment, the storm has entered fully into the magnetosphere and ionosphere. The atmosphere glows, currents flow, Earth's magnetic field shifts with slow precision. Yet even now, the deepest consequences have not yet reached the ground. That phase quiet but powerful lies ahead. For now, the narrator lingers in the upper atmosphere, sensing the height of the auroral energy, the steady arrival of particles and the planet turning under a storm that it cannot feel, but that transforms its sky with ancient steady brilliance. The narration drifts downward, now sinking from the luminous ribbons of the aurora into the quieter layers below, where the storm's deeper influence unfolds without light. Here the guiding sensation becomes the slow transmission of energy from sky to ground, an unseen descent as geomagnetic currents flow through the ionosphere, induce electric fields at Earth's surface, and seep silently into the technological systems built upon the planet's crust. No sound accompanies these changes. No flash or vibration announces them, yet the storm begins to press into the world's conductive materials with patient precision. The scientific fact grounding this section is that geomagnetic disturbances induce electric currents in long conductive systems, power grids, pipelines, telecommunication cables, because fluctuating magnetic fields create electric fields in Earth's surface. Only took the quiet shifting of a planet's magnetic field to send currents flowing through wires and soil. As the narrator moves through the upper atmosphere, the auroral electrojets strengthen, further flowing in broad arcs around each pole. These currents shift, expand, and contract as particle injections continue. Every movement of the electrojets alters Earth's magnetic field, causing fluctuations detectable even thousands of kilometers away. These fluctuations extend downward through the atmosphere as quasi-static changes in magnetic structure, inducing electric fields along the ground. Only took a drift of electrons high above the clouds to shape voltages felt deep in the crust. A poetic detail emerges in the way these induced electric fields spread across the surface. They form not in sharp lines, but in diffuse patterns shaped by the conductivity of rock soil and underground water. Regions rich in sediment or fractured crust receive higher induced currents. Regions with crystalline bedrock receive less. In narration, this appears like a faint invisible map of subterranean contours defined by long-buried geological history, now illuminated by the silent touch of a solar storm. Only took the memory of ancient rock to determine how a star's energy moves through a world. Yet a scientific uncertainty lingers. Even modern models struggle to predict ground-induced currents precisely. Subsurface conductivity varies unevenly, and magnetic disturbances fluctuate across wide areas. Measurements help, but complete accuracy remains elusive. Only took the hidden complexity of Earth's interior to keep surface currents partly unpredictable. As the narrator descends toward Earth's surface, the atmosphere grows denser and darker. Storm-driven winds in the thermosphere ripple downward, influencing density patterns in the upper mesosphere. Though these effects remain faint, they contribute to atmospheric tides, slow planetary-scale waves that migrate around the globe interacting with diurnal heating cycles. Only took the brushing of particles against thin air to send subtle waves through layers dense enough to hold clouds. Below the D and E regions of the ionosphere respond to increased particle precipitation. Chemical reactions intensify as energetic particles break apart atmospheric molecules, forming compounds such as nitric oxide and hydrogen oxides. These compounds influence ozone chemistry and can persist for days or weeks after a major storm. In this retelling, they feel like soft chemical echoes, quiet rearrangements in the sky's molecular composition. Only took a few collisions to leave a lingering fingerprint in a planet's upper air. As the storm deepens, communication paths change. High-frequency radio signals refract differently through the disturbed ionosphere, sometimes bending into unexpected routes, sometimes fading entirely. Navigation systems relying on ionospheric reflection degrade. Yet none of this appears with drama, only with shifts in signal clarity, subtle distortions in wave paths that form part of the storm's invisible reach. Only took a ripple of electrons to confuse signals travelling silently through the air. The narrator reaches the surface now, where the storm's influence enters the ground. In conductive materials, power lines stretched across continents, transformer cores made of metal. Long pipelines buried in soil, geomagnetically induced currents begin to flow. These currents rise slowly, proportional to the rate of magnetic field change overhead. In most storms, these currents remain modest, but in powerful events they grow large enough to heat transformer windings, push systems beyond their operating limits, or alter the corrosion rates of pipelines. Only took a star's distant flare to nudge currents in machines built for a quieter sky. A poetic image settles here. The power grid becomes a quiet mirror of the auroral electrojet. Where currents flow in the sky, faint copies flow in the ground. Where magnetic fields twist above electric fields, trace their reflections below. Technology becomes an unintentional participant in a cosmic interaction, billions of years older than wires, metals, or machines. Only took the geometry of Earth's field to couple the heavens and the grid. Yet another scientific uncertainty arises. The precise vulnerability of infrastructure varies with design geology and the timing of the storm. Ground current models rely on imperfect knowledge of subsurface conductivity and transformer sensitivity. Engineers monitor for risk, but predictions remain approximate. Only took the unknowns of rock and metal to keep preparedness partial. The narrator drifts farther across continents. Under polar skies, strong ground currents flow through soil and rock, entering long transmission lines. In mid-latitudes, the effect is weaker but still present. Transformers compensate automatically, though the additional load causes subtle thermal changes. None of this poses immediate danger in the current moment. The storm remains strong but not yet extreme. But the processes unfolding now reveal how a more powerful event such as the Carrington storm of 1859 would reach even deeper. Only took a moderate storm to hint at the scale of what a stronger one could do. Meanwhile, overhead the aurora grows brighter. Arcs intensify, expand, and break apart into dynamic structures. Curtains ripple with increased speed. Pulsating patches flicker across the night. The magnetosphere channels energy downward as though the sky breathes in cycles, brightening, dimming, brightening again. But here on the ground, only faint signs offer clues. Instruments detect shifts, compasses tremble slightly, signals waver. Only took a sky full of shimmering currents to move a needle made of iron. As the narrator moves near, coastlines-induced currents behave differently. Saltwater conducts electricity far better than rock. Coastal regions experience stronger ground currents because the contrast between land and sea shapes electric field distribution. Submarine cables respond to these variations, feeling the storm through increased voltage differences across long spans. Only took the meeting of water and rock to shape how a star's outflow moves into a world's edge. The storm's influence reaches even underground pipelines. Long metal pipelines form conductive paths that absorb geomagnetically induced currents, altering corrosion control systems. In this quiet retelling, the effect appears not as degradation but as subtle imbalance. A small shift in voltage, an extra nudge in the long steady processes working at depths unseen. Only took a cosmic pulse to touch a pipeline buried beneath soil and stone. And yet beneath all these effects, Earth's surface remains calm. Winds blow normally. Rivers continue their flow. cities glow with artificial light, forests sleep in their nighttime stillness. No creature senses the currents passing through iron or the chemical shifts occurring miles above. The storm's grandest interactions remain hidden in the machinery of fields, currents and particles. Only took the veil of atmosphere and rock to turn cosmic turmoil into surface quiet. The narrator rises once more up past the rooftops through the troposphere beyond the stratosphere until the glowing aurora appears again overhead. The storm's midpoint has begun to pass. Energy flows steadily but without the peak intensity still to come. Earth remains wrapped in a luminous ring. The magnetosphere pulses. The ground responds with its own quiet currents. The upper atmosphere breathes with new chemistry. And all these processes unfold in patient synchrony, with deep calm beneath the complexity. Only took a world turning under a star to maintain serenity amid a cosmic storm. And so the narrator hovers in this quiet balance between sky and ground, between particle and wire, between cosmic cause and terrestrial response. The deeper phase of the storm waits ahead, where the ring current will strengthen, further auroras will expand brighter still, and Earth's magnetic field will reach its largest deviations. But for this moment the storm rests in a middle quietness, not at its beginning, not yet at its height, but in the steady unfolding of forces that shape both atmosphere and ground, in ways subtle yet unmistakable. The narration rises gently from the quiet surface currents and ascends once more into the vast magnetic architecture surrounding Earth, where the storm's deeper phase approaches with slow, inevitable gravity. Here, the guiding sensation becomes the strengthening of the ring current, a silent torus of drifting ions encircling the planet, whose subtle expansion marks the transition into the storm's most geomagnetically significant stage. The processes remain smooth, unhurried, driven not by sudden impulses, but by a steady influx of energy delivered by the CME pressing continuously against Earth's magnetic shield. The scientific fact grounding this moment is essential. The ring current, composed of charged particles drifting westward around Earth, weakens the planet's magnetic field during geomagnetic storms, producing the characteristic drop in the Deist index used to quantify storm intensity. Only took a belt of drifting ions to nudge a planet's magnetic strength downward hour by hour. As the narrator drifts into the inner magnetosphere, the ring current becomes more defined. Its population of ions grows fed by injections from the magnetotail, and convection flows from the outer magnetosphere. Oxygen ions, heavier and more energetic, begin to dominate this stage of the storm, drifting slowly yet persistently around Earth. Each particle follows a path shaped by the curvature and gradient of Earth's magnetic field, completing circuits that contribute to a global current flowing far above the atmosphere. Only took the slow orbit of ions to carve a current ringed around a turning world. A poetic detail emerges in the way these ions drift. Their motion is not smooth, but a quiet combination of gyration, bounce and drift, the three characteristic movements of charged particles trapped in Earth's field. Viewed abstractly, they form graceful spiraling paths rising and falling along magnetic lines as they circle the planet. In narration, it feels like the slow weaving of an invisible tapestry, with each particle tracing its line across a dark, silent canvas. Only took a particle's wandering to stitch patterns through a magnetic night. Yet a scientific uncertainty lingers. Despite decades of research, the ring current's exact composition during major storms remains difficult to measure. Instruments aboard satellites identify the general populations of ions, but distinguishing their precise sources, solar wind ionosphere or magnetosphere, remains challenging. Only took the overlap of particle origins to blur the boundaries of what flows through the current's quiet arc. Below the drifting ions, the atmosphere reflects the storm's growing influence. Thermospheric temperatures rise as auroral energy spreads across high latitudes. Air density increases at satellite altitudes, altering drag and shifting orbital paths slightly. These changes unfold, gradually expressed not as sudden jumps but as steady thermal expansion. Only took the gentlest heating in thin air to nudge satellites circling far above oceans and continents. The narrator moves closer to the ring current's outer edge, where energetic electrons drift eastward in counterbalance to the ion's westward drift. Together, these motions create a complex interplay of currents. Electric fields arise from charge separation. Magnetic fields adjust in response. The system behaves as a coupled circuit spanning tens of thousands of kilometers. Yet in narration, it feels like a quiet balancing act, forces adjusting in harmony currents, growing with soft inevitability. Only took a star's distant breath to set vast circular paths of energy in motion. The magnetic field at Earth's surface responds subtly. Its strength decreases across many latitudes. Ground-based magnetometers detect smooth downward trends in field intensity as the ring current strengthens. These changes will eventually be recorded as negative det values. But here, drifting above Earth, the narrator senses only a soft loosening Earth's magnetic grip relaxing as the storm continues. Only took a world's outer cocoon easing slightly to signal the storm's halfway point. Above the magnetosphere remains compressed by the CME, its dayside boundary pushed inward like a shell pressed by steady wind. Reconnection continues along the magnetopause, allowing more solar particles to enter. These particles join the plasma sheet drift inward and feed the ring current. The storm intensifies not through forceful shocks, but through sustained pressure, through a slow, continuous inflow of energy. Only took hours of quiet compression to deepen the storm's magnetic imprint. A poetic image arises as the narrator moves into the region, where the ring current overlaps with the plasmasphere. The plasmasphere, once smooth and rounded, stretches into a plume extending sunward. The edges of this plume trace pathways where cold plasma flows outward, altering reconnection efficiency at the magnetopause. In visualization, the plume appears like a gentle extension of the atmosphere, a soft tongue drifting into space. Only took a plume of cold plasma to influence how the sun's energy slips into Earth's magnetic field. Meanwhile, the aurora brightens further. The magnetotail continues sending bursts of energized particles earthward. These injections create substorms, localized intensifications of auroral activity superimposed upon the broader geomagnetic storm. Curtains of light ripple more quickly, arcs fold upon themselves, and diffuse patches brighten across the sky. Yet from afar, these motions appear orderly, as though the aurora breathes gently in its expanding glow. Only took the collapse of tailfield lines to lift the sky into larger waves of colour. A scientific uncertainty lingers gently. The exact mechanisms that separate substorms from storms remain debated. Though both result from reconnection, their timing triggers and interactions with each other are not always aligned. Some storms contain many substorms, others proceed quietly. Only took dynamic variability to turn space weather into a field of ongoing mysteries. The narrator drifts toward the outer radiation belt now, where storms induce deeper changes. The outer belt, populated by high-energy electrons, becomes enhanced during some storms and depleted during others. In severe cases, radiation levels increase dramatically, posing hazards to satellites. But in this moment, the belt responds with subtle shifts, electrons driven inward, outward, or lost to atmospheric precipitation. Only took the drift of high-energy electrons to reshape the radiation belts encircling a world. Below, the upper atmosphere continues to heat. Neutral wind patterns adjust, forming new circulations that carry heat toward lower latitudes. These circulations interact with tides driven by solar heating, producing complex patterns of motion. In narration, these patterns feel like quiet atmospheric currents, broad, slow winds moving unseen through thin, cold air. Only took the warming of high latitudes to ripple through the atmospheric layers far below. As the ring current strengthens, Earth's magnetic field drops further. The surface sees larger deviations. Compasses drift by small degrees. Instruments register changes that remain invisible to ordinary human senses. The geomagnetic disturbance becomes global, a signature of the storm's deeper progression. Only took the drift of particles circling a planet to change magnetic headings in distant cities. The narrator moves eastward across Earth's darkened hemisphere. On the ground, the night remains quiet. Forests rest. Oceans darken. Cities continue their stillness. But above the aurora stretches farther south, reaching latitudes that rarely see such light. From space, these lights form wide bands, luminous rings circling both hemispheres, shimmering softly as Earth turns beneath them. Only took the alignment of field and storm to send the lights wandering far from their polar routes. The ring current reaches its peak, strength gradually, not abruptly. The Deist index drops toward its minimum, reflecting the storm's intensity. In a Carrington-scale event, that drop would be enormous. But here the narrator focuses on the physical processes, not the historical magnitude. The weakening of Earth's field represents the quiet culmination of hours of drift injection and convection. Only took the slow drift of ions around a planet to reshape its magnetic environment. A poetic detail settles in the overlapping layers of geomagnetic structure, the ring current, the plasmasphere plume, the auroral electrojets, and the radiation belts all interact in delicate ways. Their couplings form a single, vast, interconnected system, one that responds to solar pressure with patterns elegant in their complexity. Only took the dance of fields and particles to reveal a harmony no surface storm could match. As the narrator pulls back, the entire magnetosphere appears altered, compressed, energized, glowing, shifting. Earth rotates silently within it. The storm continues but has not yet begun its recovery. The next phase will involve gradual relaxation currents, weakening fields returning to steady strength, particles redistributing. But that lies ahead. For now, the storm remains at its geomagnetic height, balance between injection and release between pressure and response. The world turns in quiet harmony, enveloped by a storm whose brilliance illuminates its skies, and whose influence reshapes its invisible shields with slow, steady certainty. Only took the breath of a star reaching across space to bring a planet into this calm, luminous middle of a cosmic event. The narration rises once more above Earth's glowing poles, sensing the storm entering its long, slow unwinding. Here the guiding sensation becomes the planet beginning to recover from the solar disturbance, with currents easing, fields stabilizing, and the vast magnetic architecture relaxing into simpler shapes. Nothing ends abruptly. Instead, the storm softens with a patience equal to the time it took to rise. The CME continues drifting outward into the heliosphere, leaving behind a magnetosphere that must now redistribute energy through gradual quiet processes. The scientific fact grounding this stage is that geomagnetic storms decay as the ring current weakens, a process governed by charge exchange, wave-particle interactions, and the slow leakage of energetic ions into interplanetary space. Only took a world-sized drift of ions to weaken, then quietly fade as the storm moves toward its close. As the narrator drifts into the inner magnetosphere, the ring current shows its first signs of decline. Oxygen ions, once dominant, begin interacting with cold hydrogen atoms in the extended atmosphere. These charge exchange reactions neutralize some energetic ions, allowing them to escape the magnetic trap. Over time, this process reduces the current's strength. In narration, these escapes feel like quiet departures, particles slipping gently from their long drift paths into the darkness of space. Only took a small exchange of charge to free a particle that had circled Earth for hours. A poetic detail emerges in the way the magnetic field slowly regains strength. Ground-based observations would show a gradual rise in the Deist index, marking the planet's recovery. But here, floating above Earth, it feels like a loosening thread being rewound, a soft retightening of the magnetic fabric that had relaxed during the storm's height. Only took the slow drift of energy away from Earth to let the field breathe back into shape. Yet a scientific uncertainty lingers. The precise timing of storm recovery varies widely. Some storms relax quickly, Others linger for days. The balance between ring current decay, continued particle injections, ionospheric winds and magnetotail dynamics remains complex. Models predict general trends, but the details of any particular storm differ. Only took the variability of natural systems to keep recovery curves imperfectly understood. Below the aurora softens, the intense flows of energetic particles lessen, curtains of light slow their motions, arcs contract poleward. The once bright ovals become narrower, returning gradually to high latitudes. Colours fade from deep greens and reds back to faint ghost-like glows. Only took the easing of magnetotail injections to dim the sky's luminous geometry. The narrator drifts downward toward the ionosphere where the storm-driven currents weaken as well. The auroral electrojets shrink in width and intensity. Their magnetic signatures at the surface become smaller. Electric fields across polar regions grow more diffuse. Conductivity decreases as particle precipitation lessens. The complex storm-time ionospheric patterns give way to quieter, more symmetric flows. Only took the decline of field-aligned currents to let the sky's electric tides return to steadier rhythms. In the thermosphere, the heat deposited by auroral activity begins to spread more evenly. Winds still carry warmth toward lower latitudes, but the high-latitude heating that drove strong circulation patterns slowly subsides. Temperatures begin to fall from their storm-time peaks. Air density at satellite altitudes decreases as the atmosphere contracts. Only took the fading of auroral input to ease the expansion of layers too thin to feel yet too large to ignore. A poetic image arises as the narrator moves through the waning aurora. The sky appears like a dimmed lantern, the edges of its once bright patterns softening into diffuse trembling outlines. The magnetosphere feels gentler. The storm's intensity becomes memory rather than motion. Only took the passage of time measured in hours to quiet a sky stirred by forces older than life itself. Meanwhile, in the magnetotail, reconnection continues, but with less vigour. The tail's stretched fields return to more dipolar configurations. Plasma flows diminish. The previously energised current sheet thickens again, becoming more stable. Substorm activity lessens, and the tail no longer sends strong pulses of particles earthward. Only took the easing of solar pressure to let the tail reform its balanced, elongated shape. Yet a scientific uncertainty settles here as well. The tail's relaxation varies with solar wind conditions, which continue to fluctuate even after the CME's main body has passed. Residual turbulence in the solar wind magnetic sector, boundaries or fast streams following the CME can all prolong disturbances. Only took the variability of space weather to stretch a storm's quiet exit across unexpected hours. The narrator ascends again into the inner magnetosphere, observing the ring current in its final stages of weakening. Wave-particle interactions become increasingly important now. Electromagnetic ion cyclotron waves scatter ions into the atmosphere, removing them from the current. Chorus waves generated by energetic electrons contribute indirectly to current decay by influencing particle distributions. These interactions feel in narration like soft murmurs, background tremors, guiding particles away from their orbits. Only took the smallest background waves to help dissipate a current encircling an entire world. Below, the atmosphere responds with its own quiet adjustments. Chemical traces produced by particle precipitation nitric oxide hydrogen oxides begin dispersing through global circulation patterns. Some descend into lower layers over days. Their lingering presence subtly alters ozone chemistry, though not dramatically in this moment. In narration, these chemical journeys feel like fading echoes, reminders of a storm's reach long after its brightness fades. Only took a shift in atmospheric chemistry to carry the storm's memory beyond its visible end. On the ground, geomagnetically induced currents diminish. Transformers experience lower induced voltages. Pipeline corrosion control systems return closer to their usual states. Communication disturbances lessen as ionospheric irregularities fade. GPS signals regain stability. To human systems, the world begins to feel normal again, though nothing dramatic distinguishes the return. Only took the quieting of a sky full of currents to let machinery breathe easier once more. The narrator moves across mid-latitudes where faint remnants of the aurora retreat northward. The horizon darkens uncluttered by the earlier glow. Stars reassert their steady presence. The atmosphere, freed from the torrents of charged particles, resumes its typical nocturnal stillness. Only took the end of a particle stream to return a night sky to its old familiar silence. Yet Earth's magnetic field still bears the storm's imprint. It will take many hours for the field to return fully to its pre-storm strength. The storm recovery phase is gradual, governed by the slow decay of currents spread across vast distances. The narrator senses this lingering softness in the field, a slight remaining looseness in its lines as though the magnetosphere is still stretching after a long deep breath. Only took a world's magnetic architecture time to gather itself again. A poetic detail emerges in the polar cusp regions where the storm's final particles slip through with decreasing frequency. These cusp funnels open to interplanetary space grow quieter, their once bright precipitation softening into faint intermittent flickers. Only took the closing of magnetic windows to end the rain of particles from a passing star. As the magnetosphere settles, Earth's rotation carries the world beneath the diminishing storm. Daylight approaches on one side, night deepens on the other. The storm's long arc becomes memory first in the aurora, then in the currents, then in the drifting ions that slowly disperse. Only took the turning of a planet to fold the storm into the rhythm of time. The narrator pulls back, now sensing the global calm returning across skyfield and ground. The storm is ending, but its story is not complete. Ahead lies the reflection of what such events mean, how they reveal the deep connection between a star and the planet it illuminates. And soon the quiet wind down will settle everything into the stillness that follows cosmic motion. But for now, the storm rests in its final unwinding, with the magnetosphere relaxing, the currents softening, and Earth returning slowly to its quiet equilibrium under the distant steady light of the sun. The narration lifts gently above the now quieting Earth, where the magnetosphere stretches once again into its familiar configuration, softened but recovering. Here the guiding sensation becomes reflection, without conclusion, an extended breath, after the slow unfolding of the storm where the sun's influence lingers in memory more than motion. The magnetic field lines no longer strain, the currents no longer surge. Instead, everything settles into patterns shaped by the storm but no longer driven by it. The scientific fact grounding this final section is that even after a geomagnetic storm subsides, Earth's space environment remains altered for days. Radiation belts reconfigure, the ionosphere settles slowly, and the magnetosphere holds the imprint of the disturbance long after the particles and fields have eased. Only took a few hours of cosmic pressure to shape days of gentle recovery. As the narrator drifts across the magnetosphere, the layers of energy reveal their gradual return to equilibrium. The radiation belts adjust first as high-energy electrons diffuse outward or precipitate into the atmosphere. In the outer belt, populations depleted by wave-particle interactions slowly rebuild through interactions with the solar wind. The inner belt remains largely unchanged, its stability a quiet contrast against the dynamic outer regions. Only took the lingering hum of space waves to reshape regions filled with particles older than any human structure. A poetic detail emerges as the plasmasphere rounds out again. During the storm, it stretched into a long sunward plume. Now that plume contracts, smoothing back into the familiar teardrop shape that envelops Earth. Plasmaspheric hiss, natural radio waves produced by the movement of cold plasma, fills the inner magnetosphere again. A faint and constant whisper, too soft for human ears but unmistakable to satellites. Only took the return of cold plasma to fill the magnetosphere with its gentle, unending murmur. Yet a scientific uncertainty lingers. The timeline for plasmaspheric recovery varies, widely influenced by the solar wind conditions that persist after the storm. Fast streams behind a CME can prolong disturbances, while quieter solar wind hastens recovery. Only took the variability of the solar wind to keep the end of a storm as uncertain as its beginning. The narrator descends toward the ionosphere where the storm's chemical imprints begin to disperse. Nitric oxide created during particle precipitation migrates downward, eventually influencing ozone chemistry in the middle atmosphere. Hydrogen oxide radicals also drift into lower regions, participating in reactions that subtly shift atmospheric composition. These changes are not dramatic, they unfold quietly over days and weeks. Only took a handful of high-energy collisions to leave a fading trace in layers of air unseen. In the thermosphere, temperatures gradually decline after their storm time peaks. Winds slow, density decreases. Satellites encounter less drag. The atmosphere contracts gently toward its pre-storm state. That contraction, though invisible from the surface, marks the gradual cooling of a layer heated by the auroral energy that once surged through it. Only took the fading of light in the polar sky to cool an atmosphere stretched too thin to feel. The narrator moves farther downward, where the D and E layers of the ionosphere regain their usual balance. Storm-driven ionization dissipates. Sporadic patches of enhanced density fade. Radio waves travel more predictably. Navigation systems regain clarity. Communication paths return to familiar patterns. Only took the quiet settling of electrons to restore the sky's transparency for waves that move unseen. Meanwhile, the ground reflects the storm's final echoes. Geomagnetically induced currents weaken until they fall below detection thresholds. Transformers release their thermal loads, returning to cooler states. Pipelines revert to their usual corrosion control patterns. During the storm, these systems felt the faint touch of solar influence. Now they settle back into Earth's own rhythms. Only took the easing of magnetic fluctuations to let technology rest again. The narrator rises once more above the poles where the aurora has shrunk into a thin band hugging high latitudes. The colours that once filled the night sky fade into faint glows barely visible in the dark. These lights will intensify again during future storms, but for now, they quiet themselves into a dim reminder of the energy once flowing along Earth's magnetic field lines. Only took the planet's rotation and the storm's decline to fold that brightness back into night. Now drifting above Earth's dayside, the narrator senses the solar wind returning to calmer patterns. The CME continues its outward journey long past Earth, now travelling into regions where the heliosphere widens toward interstellar space. Its structure, once compact, now vastly expanded, merges gradually into the background solar wind. Only took the passage of a single cloud of plasma to remind a planet of its connection to a star. A poetic detail settles in the sun's steady light. After the flare, after the CME, after the geomagnetic storm, the sun's radiance returns to its familiar calm. Its surface continues to granulate. Loops rise and fall. Sunspots form and decay. The star remains dynamic, yet the light that reaches Earth appears unchanged. Only took a star of constant motion to offer a world the appearance of stillness. Yet another scientific uncertainty lingers. Even with advanced observations predicting storms at Carrington scale remains difficult. The precise magnetic orientation of a CME, the interactions it encounters en route to Earth, and the conditions of the magnetosphere at arrival all influence outcomes. Only took the interplay of countless variables to keep space weather forecasting an evolving science. As the narrator drifts outward into the orbit of the Moon, Earth's magnetosphere appears delicate yet resilient, shaped by invisible forces, but always returning to equilibrium. The long tail stretches nightside, its shape restored. The dayside boundary expands again as the pressure from the solar wind decreases. The entire magnetic structure breathes slowly, matching the rhythm of solar conditions far beyond human control. Only took the balance of a planet's magnetic field to maintain calm after a cosmic disturbance. From this vantage, Earth resembles a quiet world wrapped in an invisible shield, a shield that flexes and bends but holds shaped by interactions that began with a distant release of energy on the sun's surface. The storm has passed, leaving only its subtle imprints across skyfield and ground. But those imprints reveal a truth ancient as the sun itself. Earth and its star remain in constant dialogue, their histories intertwined through flows of light heat and charged particles. Only took the journey of a solar storm to glimpse the bond between a star's breath and a planet's gentle resilience. The narration floats still farther outward now, preparing to settle into the wind down that will quiet the final currents of thought. Earth rotates steadily, its recovering magnetosphere glowing faintly at its poles. The sun shines with its usual calm. Space stretches in all directions, filled with the slow drift of particles born in a furnace of fusion before crossing millions of miles to touch a world. And all of it unfolds without rush, without drama, just the smooth continuation of processes older than continents and oceans. Only took the patience of the universe to hold this moment in its quiet, endless rhythm. The narration drifts far from Earth, now letting the planet shrink into a soft sphere wrapped in faint auroral haze. The guiding sensation becomes not motion, but release the easing of every process that carried the storm across space through atmosphere and along magnetic pathways. Nothing pushes forward anymore, nothing builds. The solar wind resumes its quiet flow past the world, and the magnetosphere holds steady, not strained, not compressed, just balanced beneath the gentle pressure of a calmer star. Light from the sun reaches Earth with its usual patience, crossing the same 8 minutes. It always has, unchanged by the storm that moved through the system. Only the memory of the disturbance lingers woven into the layers of plasma and field now settling back into their enduring shapes. Below the atmosphere rests. The faint traces of chemical shifts disperse into broader circulations. Winds in the thermosphere slow and cool, drifting into silence like breath settling after effort. The ionosphere regains its familiar clarity, letting signals pass more cleanly through its layers. All the complicated interactions, currents, rising particles, falling fields, reconnecting, fade into softness. The variations that once spanned continents now narrow into the thin, high-latitude regions shaped by ordinary polar light. With each passing hour, the auroral glow dims into a narrow ring that circles the poles without urgency, like a quiet reminder of the storm's distant origin. Farther above, the magnetosphere extends into its long night-side tail, smooth and relaxed, no longer taut from solar pressure. Its lines stretch without strain, held by the balance that has guided them for billions of years. The ring current weakens into insignificance its drifting ions, no longer imposing their gentle weight on Earth's field. The plasmasphere rounds itself into calm symmetry, its edges no longer tugged by storm-time convection. The radiation belts continue adjusting in slow, almost imperceptible ways, but the storm's imprint grows fainter with every circuit of particles around the world. Even the ground with its networks of metal and stone grows still. Induced currents fall to nearly nothing, leaving transformers, quiet pipelines stable and soil undisturbed by the passing of electric fields that carried part of the sun's energy into the Earth for just a moment. The world systems feel ordinary again, though the memory of subtle shifts remains in their long patient materials. The narration drifts outward until Earth and Sun share the same quiet frame suspended in the wide and nearly silent heliosphere. The Sun glows gently, its granules rising and falling, its magnetic loops arching and dissolving. Nothing about its present light hints at the flare or the CME that began this journey. Even so, the processes continue deep and ongoing, part of the endless dynamics that shape the star's rhythms. Earth turns beneath that steady glow, a world with a magnetic shield that flexes and reforms, always ready to shift in answer to the star that warms it. Nothing feels urgent now, nothing leans forward. The slow unspooling of a geomagnetic storm has passed into stillness, and what remains is the broad ancient quiet that holds the spaces between events. The narrator lets that quiet deepen. Light drifts, space breathes, Earth holds its orbit with calm precision. And in that long, gentle pause, the storm becomes only one more moment in a story measured across ages, an age-old exchange of energy between a star and the world that circles it. There is nothing left to follow, nothing left to anticipate, only the return to the soft, enduring rhythm that carries planets, winds and fields through the slow rotations of time. The narration settles into that rhythm, letting the quiet fill every motion, every field line, every last trace of the long journey just past.